Hi, everyone. I'd like to welcome you to the last installment of the third season of the Young Researchers Forum. Today's presenter is Sebastian Rodriguez Rosero, hailing from McGill University in Montreal. So Sebastian is an undergraduate student in honors mechanical engineering at McGill University. As a research assistant at the Thermodynamics and Combustion Group, Sebastian has conducted research on gaseous detonations using high-speed optic diagnostics and numerical modeling techniques, focusing on the behavior of imploding detonations under various conditions. That's what he'll be talking about today. In addition to this, Sebastian was also involved in a groundbreaking study that investigated laser thermal propulsion. In the study, he focused on the aerothermodynamics, thermodynamic analysis of a Mars aero capture maneuver, and also optimizing the aerodynamics requirements for interplanetary missions within the solar system. So currently, Sebastian is a member of the cryogenics team at Anion Systems, a quantum computing firm. And in this role, he's exploring the limitations of thermometry at ultra-low temperatures. So, Sebastian, thank you for agreeing to join us. It was good to see you last year at the Canadian Symposium. So, if you'd like to share your screen and begin.
Yeah, well, thank you very much for the introduction. I will begin my presentation. Hope that everyone can hear me well. Just 1 second. Okay, I hope that you see my slides. Yeah, okay.
That looks good.
Okay, so well, hello everyone. As Shem said, I will be talking about our study focusing on the mechanism that drives the symmetry of imploding detonations, particularly when they propagate through thin channels. So I begin with an introduction to our presentation. We have a short introduction to the topic, description of the experimental apparatus, our results, our numerical model that we've used to explain or understand these results, a comparison between these results and the numerical model, and finally, what I would say are quite beautiful pictures that we've captured of the imploding detonations. So first of all, why imploding detonation waves? So as probably everyone here knows, detonation waves are means through which the thermodynamic properties of a medium are increased. Now, if you take that energy release and you focus it into a very small region, you're able to create a very high energy state. And several people, including, for example, Terra et al., have studied how to use this energy density state to initiate fusion reactors. And others, for example, Jackson et al., have studied how to use these imploding detonations as efficient initiators for fuel air engines. So essentially, everywhere where you might need a high energy density state with a relatively low energy input, imploding detonations can be useful. So the implosion phenomena was first studied in shockwaves. So the first, or one of the first studies, was the one by Perry and Kantrowitz in 1951. This was done in this cylindrical shock tube with a tear-shaped obstacle at the end. And so Perry and Kantrowitz were the first to really try and form imploding shockwaves through diverging or shaping initially planar shocks. Later on, Saito and Glass in '82 used their hemispherical cavity to quantify the energy density at the focal point. They've measured through spectroscopic measurements temperature at the center of upwards of 10,000 Kelvin. And more recently, others like Hilander et al. Have started forming polygonal converging shockwaves in facilities similar to the one done by Perry and Kantrowitz in 1951. Now, there are several other studies for this, but most of these were very well documented in the recent book by Eliasson and Epicedes, Shock Focusing Phenomena. On the other hand, imploding detonation experiments are quite scarce. Most of these were done at McGill during the 1960s and 70s by the group of Lee and Knystautas. So what we see here are actually the three experiments that they lunges where you initiate the detonation on one side and it's forced to converge at the other. And later on, they attempted different things, like, for example, initiating these imploding detonation as a series of polygonal smaller detonations, or using what is in the last figure in 1971, an annular shock tube. And then the bottom, you can see some of the footage that they reported. Now, throughout these different studies, several aspects of imploding detonations have been documented, and this concern their stability, initiation, and usefulness. However, although it was noted that producing highly symmetric imploding detonations is very difficult, we have not yet established what the exact mechanism that causes this asymmetry is. So for this reason, the topic of this research is to try and identify this mechanism. And we've done this through, as was mentioned, high-speed videography, numerical modeling, and we've also used this open shutter method to visualize the cellular structure of these detonations. So we begin talking a bit of our experimental apparatus. So if you look on the right, we see that our facility is very similar to the one built by Lee and Lee in 1965. Now, this was done because this experiment is comparatively simpler to manufacture than the other iterations of their experiment, and this allows us to try very different things to try and improve the symmetry of these converging detonations. So if we focus on the diagram on the right, we see that the detonation is starting at a detonator that we have on the bottom of our experiment. You can see it also on the render. So the detonation is starting here. It is started with the spark igniter, and then it travels upwards into the cavity, where it is forced to diverge because of a center disk wraps around said disk, and is helped with the curved walls, and then converges on the top, where we are able to film it with a Shimatsu HPVX2 camera around 1 million frames per second. In the diagram, you can also see some of the plumbing that we've used to both make the test mixture and controlled experiments. Now, there are two mixtures that we have used for the results that you will see in this talk. We have experimented with different mixtures, but we have focused in using acetylene oxygen because of its ease of initiation and small cell size. Now, for the test mixture, we have used the stoichiometric acetylene oxygen, simply because there is previous data that we've used to compare to our results, and we have equimolar acetylene oxygen for the pre-detonator. This was simply done because we want to ensure that a prompt initiation or fast DT is occurring before the detonation enters into the cavity, just to ensure that, again, they're as symmetric as we can make them. If we now get a close-up into the inside of our experimental facility, we have several things to note. So for example, we see that we have the glass window on top. We have this center disk that I've mentioned helps us redirect these detonations into converging. And then we have a support structure that supports this disk. Now, the exact geometry of this support structure, because it is in the way of the detonation as they enter through the small inlet at the bottom, is of importance, and we will be briefly talking about the steps that we've taken to minimize their impact on our experiments. So, as I just said, we have used several iterations of the support structure because of its influence in our results. So our first iteration was this support cylinder that is seen on top. This is a cylinder with 6 diverging channels that we've created first in the hope of protecting this structure from the incoming detonations. And then a second generation where we've used 6 individual airfoils. These are symmetric and have an extended trailing edge. And we have decided to use the shape simply because it minimizes the separation of the detonation front as it propagates through the supports. Now, if we talk about the test section geometry, we have some of the main dimensions here on the left, and we have what we call the wave shaping insert Now, this is a piece that rests on top of the center disk that I've been talking about. And we use this simply because of the shape of this experiment, when we force these detonations to converge, we're introducing some three-dimensional instabilities in the form of sloshing. And this is something that is not desired for our experiment. So by reducing the channel thickness to the order of a couple of millimeters, we're essentially able to treat these imploding detonations as almost two-dimensional. And this is something important for analysis. Now, something of relevance, you will notice that the side profile of this wave shaping or wave cutting insert that we've created is tapered. Now, this was intentional so that we can almost split the detonation into two, with the smaller front coming into the test section and the rest being redirected away. This feature is something that you will see in all of our tests. Now, I'm about to show you one of our videos. So this video is with a constant channel width of around 2.3 millimeters. The initial pressure before initiation is 30 kilopascals, and we're using a pre-detonator pressure of 200 kilopascals. So some relevant features to talk about is that you will notice that as the detonation enters into our test section or above this wave shaping insert, we see that some of it enters and the rest is being reflected outwards. Now, you will notice that there is a hexagonal shape at the center. Now, this is simply an insert that we placed at the center of the apparatus to prevent the window from excessively bowing. And this was necessary simply because as the channel width is so thin, and because of the low pressure at which we carry this test, the test section width might change a little bit if we allow it to bow. So this was simply a protection. And you will see this insert in several of our tests. Now, as I mentioned before, the geometry of the support structure will actually influence significantly our results. And this is, of course, something that we don't want as we're trying to produce the most symmetric imploding detonations as possible. So if you look at this series of shots, we're actually comparing the performance of our experiment with the support cylinder, which you see as the array on top, and the support airfoils. Now, interestingly, as you can see here, because of the cylinder separated channels, we are actually imprinting a specific shape into the converging front. We see that it has taken a six-sided geometry that is still visible until very late in the convergence. On the other hand, by minimizing the separation of the front, thanks to the airfoils with extended trailing edge, we are actually able to mitigate, if not completely reduce, the effects of the support structure. And we see that the front is now quite symmetric as it converges down to the test section. Now, I want to talk about what the data that we're extracting from our videos actually is. So in order to do this, we've used a MATLAB script that we created, and using an edge finding algorithm, we're able to fit exactly where this detonation front is at all times. And we've used this to get several parameters out of our videos. So these are divided into two. So first, the geometric parameters that you see on the left. So we have three of those, and the first is the off-center. So we've quantified this as the distance between the center of the apparatus and the centroid of this shape bound by the converging front. You see it here, and then further on, we have the azimuth, which is simply a measure of where this off-centering is happening. So it's an angle that tells us where, as in, for example, the face of a clock, where this off-center is migrating to. And then finally, we have the symmetry ratio. This ratio is simply telling us how well this imploding front is approximating a circle. So as it reaches unity, we take that as it is completely symmetric. And we've used this again to quantify how symmetric the detonation is and changes as it converges. Now, On the other hand, we've used this same algorithm to track the front at different points. And we've done this to estimate the detonation velocity of the converging detonations in a process similar to what we see here. So we're essentially just taking slices of each of the frames and then tracking the position to estimate the velocity. So the main driving parameter that we've used to change our experiments is of course the initial pressure before initiation. However, we've decided to plot all of the data that I will show you now in over a range of the channel width divided by the cell size. Now, we've decided to do this because what we're interested in is knowing how, by changing the number of cells that fit within the channel, these detonations are reacting different to the geometric conditions inside of these thin channels. So the following are a series of tests that we carry on with a constant channel width, so less than around 6% variation with 2.3 millimeter width at the test section. And the three plots that you see here correspond to the three geometric parameters that I just described. So the symmetry ratio on top, the off-center at the center, and then the azimuth at the bottom. So if we begin talking about the symmetry ratio, we see that over a range of cells within the channel, this is quite stable, which is, again, makes sense because in theory, everything in the section is uniform, around 0.9. Now, if we move into the off-center, a more interesting trend starts to appear as you decrease the number of cells. So we see that the off-center is quite low for a large number of cells, and then starts to almost on 5 millimeters of off-center. If we now look at the azimuth, we see that if you have a large number of cells, or we have a lot of variation in the azimuth, and then this starts decreasing as we reduce the number of cells. This makes sense because as you are very close to the center, then it becomes harder to track exactly where this implosion is, which explains the high, the large error bars in our data for the azimuth when you have many cells. Now, we can now look at the velocity that was estimated for the front. We've done this, we call the wide or thin side of the detonation. So the red is using NASCAR code for the same mixture. Now, what we see here is, first of all, we have a high degree of fluctuation between the measurements. Now, this is expected because of the angular nature of the detonation front, and the limit is expected as we see highly symmetric detonation waves. What I'm showing you here is essentially a polar plot, which by using our azimuth and how many cells fit within the test section. Now, what is interesting here is that when you have many cells, as I explained before, all of them seem to be positioned right at the center. But then as you reduce them, the off-center starts, or the center of implosion starts migrating in this particular direction. Now, it is too early at this point to call any judgment on why this might be, but it at least leads to a potential bias in the way that, so for this reason, we've decided to carry on a new series of tests. Now, for this test, we've taken our wave shaping that defines our test section, and we've intended side that is much thinner than the other. So if there is any bias that is introduced into our imploding detonations because of the geometry of our section, then we should see a heightened influence in our results. In order to quantify how cells. We've also done the same test with two different test sections. So one of them is 204 meters, and then there is a slightly larger 254 millimeter test. And we'll show you
Sebastian,
the test one after the other. Yep.
sorry to interrupt. It's a bit slow and breaking up, so maybe if you turn off your video, it'll give you a little bit more bandwidth to broadcast. Thanks.
Can you
So
hear me better now?
a little bit better. Let's see how it is.
Okay, that is unfortunate. So I'll just, I guess, repeat what I was just saying. So we're now showing a series of tests where we've intentionally canted our test section. We have one side that is significantly thinner than the other, and this allows us to test whether there is any influence of our experimental apparatus into our results. So
Yeah, it's sounding a lot better now.
sweet. Thank you for letting me know. So before I show you the data, I wanted to show you a series of tests. So this is over a range of pressure between 5 and 40 kilopascals. So on the top left, you will see the lowest pressure, and then on the bottom right, you will see the highest. And this was done again with the canted test section. This tests were done with the larger also test section, so 254 millimeters. And be sure to notice that this hexagonal piece is still at the center, so not the detonation. It's a insert that we placed there for safety. Okay, so we still see the detonation is cut by the insert, but what is perhaps more interesting is that if you compare it to the previous video that I showed you, these detonations have now taken a more elliptical shape, and this the semi-major axis of this ellipsis seems to be aligned in a very particular direction. And this is something that we see throughout the range of tests that we carried. Some other things to notice is that when you reduce the pressure a lot, so around 5 kPa of initial pressure, we start seeing that the fronts are much more unstable, and you see these striations, which is something that we expect as we are increasing the cell size. Okay, so this was the first series of tests that we carry on with a canted test section. So this was done with the smaller insert. So if we begin with the symmetry ratio, we see again, it is still highly consistent. Now it is a bit lower than before, but everything seems to be similar to our previous test. Where things start to change is when we look at the off-center in the middle. So we see here that if you have a large number of cells, as before, we detect almost no off-center. But as you decrease the number of cells within the channel, then this off-center is starting to grow rapidly until the point where it reaches almost 15 millimeters in comparison to the previous 5, simply by canting the test section a little bit. And finally, we see the azimuth. In case you don't remember, so for the constant test that I showed you, the azimuth tended to vary a lot because we were very close to the center. However, the azimuth in this case, that the test section was canted, seems to be quite uniform, around 160 degrees for all of our tests. Now, this is something that I forgot to mention before, but each one of these data points is the average of at least 3 tests, and the error bars correspond to the standard deviation between these tests. Now, what is perhaps more interesting is if now we look at the velocity estimation of, again, 2 sides of the detonation front. So if we look at the blue line, or the blue data set, we see that this is the wide side, and it is still relatively constant. It follows a similar trend as the expected CJ speed. However, now in the thin side, we're actually noticing a significant velocity deficit that is increasing. So we're reducing the detonation velocity as we reduce the number of cells. So again, perhaps too early to call in conclusions, but we're seeing at least a correlation between this off-center that we've detected here on the left and a change in the velocity of the detonation here on the right. This table simply quantifies how much we've canted the test section as you move away from the center of the test section. So this is our second series of tests with varying width. This was done with the larger insert, so it's 254 millimeters instead of 204. Now, symmetry ratio still quite constant, slightly smaller than constant with tests. In terms of the off-center, we see the same trend that we saw before with our previous canted tests. Now the off-center is not as large, but this is simply because we didn't cant the test section as much to reduce the possibility of completely closing off that test section as it was larger. And then the azimuth has, again, the similar trend where it is quite constant, this time around 140 degrees. If we now look at the velocity estimation, we see that as before, the thin side is significantly slower than the wider side, and this is particularly the case when you have just a few cells within the test section. Now, there is some variation in these results, but we believe these are mainly because of the difficulty of tracking the quite irregular detonation front in our videos that, although they are of higher resolution than usually allowed by high-speed cameras, they're still quite limited. So we're limited by the resolution of the videos that we can take. Now, if we plot this in a polar plot, so where are these different centers of convergence occurring with relation to the experimental apparatus, we see that on the left, so the smaller test section, all of these tend to follow a very consistent trend, so that, and they're oriented to the 160 millimeter mark. Now, if we change where the test section is canted now to around 140 millimeters, we see that these results are changing with them. So at this point, we're able to draw at least some preliminary conclusions where we're saying that there is a link between the geometry of the apparatus, and this link seems to be related to the velocity of the front, particularly velocity deficit of certain parts of the converging front, and seems to be also related to how many cells we have within the channel, as this off-center tends to increase as we reduce the number of cells that fit within the test section. Now, in order to test our hypothesis and shine some light on the mechanism that is causing this, hence the name of our talk, we have called on a theory that was first described by Fay in 1959. Now, this refers to the velocity deficit of the detonation front that is caused by the momentum loss to the walls, or the containing walls, as the detonation traverses because of the negative displacement of the boundary layer. So, in order to test our hypothesis that this is in fact the mechanism that is causing our asymmetry, we have devised a numerical model. Now, this numerical model, it carries on the assumption that I mentioned before, where our detonation front can be assumed to be two-dimensional. So what we've done here is to create something similar to what is called a Huygens construction model, where we are separating our detonation front into a series of smaller fronts that are traversing inwards in relation to the nearby fronts. So each of these fronts is being propagated through a forward Euler method, so it's still very simple, and is defined, the step that it takes at every time step is defined by this velocity relation. So this velocity relation was determined by borrowing the theory behind velocity deficit from boundary layer displacement that was also introduced by Fay, where we see that the velocity is changing with relation to the CJ velocity thanks to this relation here. And what this tells us that this velocity deficit is dependent on two parameters. So we have this zeta, which is the fractional increase of the area of stream tubes from the detonation front to the back of the detonation, and then this parameter epsilon. So if we first focus on the zeta, we see that it is dependent on this del star, which is simply the boundary layer displacement thickness, and then the channel width. So this boundary layer displacement thickness is a function of the cell size, the viscosity of the gas in the reaction zone, the density before detonation, and then finally the detonation velocity. So what this allows us to do is simply to have a relationship for the velocity that is dependent on the channel width, which, as I mentioned before, we believe is the driving mechanism that is causing this asymmetry. If we now talk about this other parameter, epsilon, so in phase original theory, he estimates this epsilon parameter to be around 1 to 2 for a hydrogen-oxygen mixture. However, we noticed that this was not the case for our results, and it didn't really match both our measurements and measurements done by others. For example, Ng et al., where he measured the velocity deficit as the number of cells change within the width of the channel. And in conversation with Ashwin Shinaya from P Prime, we realized that this is to be expected, as this original model proposed by Fay is assuming an adiabatic process, which is of course not the case for. So we've changed this parameter to fit much better to experimental data, as you see in this curve, where the blue line is our model carrying on with phase theory by changing this epsilon to around 12, and then it is compared with the Ng's experimental data for the same stoichiometric acetylene-oxygen mixture. This plot on the bottom is simply showing the numerical convergence, just to show that we are able to achieve convergence after around 100 elements. Okay, so if we move to perhaps the most relevant slide on my presentation, we see now a comparison between the model that we've created and the experimental results. So if we look on the left, we see that the data set and the line that match the same color correspond to the experiments that I've shown you before, and the numeric model prediction of an off-center depending on the variation of the channel width, which we've quantified but measuring the test section at multiple points. So if you can, as you can see here, we're able to match relatively well how this off-center is occurring or increasing as we reduce the number of cells within the section. And this is both the case for our smaller test section, so the blue line, and the large one, the red line. If we now look on the right, we're also able to see that we're able to at least do an order of magnitude reproduce this asymmetry that is caused at the front. Of course, because of simplifications in our model, we are not able to capture all of the very intricate geometries, but this was expected. So to draw some preliminary conclusions, we see that because of the match that we have in between our numerical model and our experimental results, we can see that the primary mechanism that is producing this asymmetry seems to be just boundary layer displacement, so losses to the walls that confine the detonations, and this is in relation to the number of cells available within the test section. We can now move to a slightly different topic. So I will show you now the open shutter pictures that we've taken of our Imploding detonations, and we have done this for various different cases, and I will talk to you about those as I show you the pictures. So this test that you see on the screen, and they look different, but this is simply because we've used slightly different settings, but we're taking a 2.5 kilopascal initial pressure for a stoichiometric acetylene-oxygen mixture. Now you will notice in blue this quite striking cellular structure of the imploding detonations, and you will notice that it is quite irregular. Now this is expected because at 2.5 kilopascals in our particular experiment, it's actually quite hard to initiate very symmetric imploding detonation. So this irregular patterns might hint to potential weakness of the detonation as it converges. Again, this hexagon that you see on the pictures on the right are simply this insert that we placed to protect the window. This was not necessary for the pictures on the left, which are the newest ones, and this is simply because we've changed our window. It's now a much thicker window, so the amount of bowing that occurs at the center is negligible. Okay, so these are 4 more tests that we've taken with an increased pressure. So this on the top left are simply tests that we've done with our cylinder, support cylinder. So there's a lot more chaos in these images. Now, if you look at the picture on the top right, these are 5 kilopascal, so quite symmetric imploding detonations, which is proven by this highly symmetric cellular structure. So, and these were particularly taken with a high pass filter, which allowed us to limit the influence of this reaction byproducts that you see in several of the images in this orange and purple colors, just to really pop out the cellular structure from the footage that we're taking. On the bottom, we've repeated this test, but with an equimolar acetylene oxygen mixture. And then on the bottom right, we have, again, 5 kilopascals with the stoichiometric mixture, but without using this filter that we place in the camera. So in conclusion, we have shown that there is a link between the geometric conditions of the apparatus and how well we can implode symmetric detonations. We have shown that this asymmetry, which is quantified by the offset and azimuth of the implosion center, is quite reproducible, and it is dependent on the number of cells available within the test section, where the fewer cells lead to a more sensitivity of this detonation as a convergence. And finally, thanks to our Huygens construction-based model, we have shown that at least this primary mechanism that drives asymmetry is the velocity deficit because of boundary layer losses at the confining walls. Okay, so I would like to thank my supervisor, Andrew J. Huygens, as well as other advisors, Charles Tianda, Jason Wasso, Ashwin Chinaya, and my colleagues at the research group, and the team at the Machine Tool Lab at McGill, who helped build our apparatus. And this work was supported by the Natural Science and Engineering Research Council of Canada and the McGill Summer Undergraduate Research in Engineering program. I would also like to thank the organizers of this forum for allowing me to present my work here. Thank you very much.
Hey, hi Sebastian, thank you very much. It seems I'm having some webcam issues, so we'll see how that goes, but can you hear me?
Yeah, I can hear you.
Okay, so thank you everyone. If you have any questions, please leave them in the chat, raise your hand, or feel free to speak up at any time. I've got a few questions for you, Sebastian, if you don't mind answering them while we wait to see if there's other questions from the audience.
Yes, of course.
My first one, I guess, if you could go to slide number 12, please.
Yes, just give me 1 second.
No problem.
I will just okay, much easier like this. Yes.
Yeah, we can see like several different waves at different distances radially, and I was wondering if you could quickly kind of talk us through what these different things that you see are.
Yeah. So this is an interesting question, because this is something that we've been actively discussing of what we think that is. Of course, behind the front, there's a lot of instability, so it's hard to perhaps always say what this referred to. But in this case, we believe that these are secondary waves that are caused once the detonation enters into the cavity. It is impacting the center disk, which is causing some reflections, and then you have additional reflections caused by this instability. So at least I think that this is what we're seeing here. It's just waves that are created behind the detonation front because of this, all of the reverberations that are occurring as the detonations enters into the cavity.
Okay, so they're created after, waves hitting the I forget what you called it, but your disk
Yeah,
that's near the window. Okay, and the edges of this channel. Okay, thank you.
that's right.
And it was also, if you could talk about your Fay model a bit more. That's on slide 27 and 28. I'm not sure I quite understood it. So what you do is you take your thickness, your instantaneous thickness, or in a certain spot based on how canted your disk is, and then you calculate the detonation deficit, and then from there you rebuild the ellipse or the teardrop front shape. Is that how it works?
Yeah, that's a way of putting it. Essentially, we're dividing these detonation front into a series of smaller fronts that are propagating in relation to each other, in the sense that we are using this inwards normal vector that depends on the angle that this front has. So it's propagating inwards, and then we're defining the velocity of each one of these fronts in relation to the width at that specific location. And this width is something that we've quantified by measuring our test section. So I didn't show it in the presentation, but we've made quite the complex jig in order to be able to measure very precisely what the channel width is at different points in the test section, and be able to reproduce that in our model.
Okay, I see. So every little section there is like a perfect 1D detonation with boundary layer losses, and then you use that to reconstruct it.
That's right, yeah.
Okay, and we have got a question from Joshua Smith, and he's asking if this is done using detailed or reduced chemistry.
So we've actually not focused on the chemistry that is occurring for these detonations. We've decided to use only the Fay model, which is really just dependent on cell size and other transport properties of the detonation. And we've done this simply to reduce the parameter space and really understand whether what is causing these issues is this boundary layer effects. There might be some interest in using a more complicated model, but we've at least shown some adequate agreement in our data with this very simple model.
Right. So you're not using any chemistry. From what I see, is you just need the heat release for your CJ detonation speed, and the cell size you're getting from the detonation database or something like that.
That's right. Yeah.
Okay. Now, Joshua, I hope that answers your question. Are there any other questions from the audience? I've got another one. I was wondering, so you're assuming that the boundary layer losses are what is causing this change in detonation velocity, but have you considered the fact that your area is also changing? So on one side you have a converging area, on the other side you have a diverging area, and that will affect how fast your detonation propagates also.
So again, I didn't include this in the talk because it was more secondary data, but we have looked into how the convergence effects influence the results. So the quick answer is that we found them not to be significant, and this is because of something that was already documented, for example, by Lee and Lee in their first paper, where for example, front acceleration because of convergence is really not significant until you're about a 20th of the initial radius of convergence. So we don't see a significant effect when we introduce this convergence. So by changing the area, as it's converging down the test section. So the results are very similar, which is why we've concluded that boundary layer losses are the primary mechanism that is causing these effects that we're seeing in our results.
Okay. Yeah, I think it probably would be too hard to add that into your qualitative model, but okay, I buy that. We have a question from Yves Balussier, and he's wondering if what the maximum pressure in the center is compared to the CJ detonation. Yeah,
so we expect it to be significantly higher because of this focusing effect, but we have not yet quantified this. It is not very trivial because the center is it's a very small part. So really being able to say what the pressure is at the exact point where it converges is not particularly easy. It might be something that we try in the future, but for now we have not looked at the pressure at the center.
Okay, Yves, I hope that answers your question, or please let me know if you've got follow-up. And if you could just go to slide 29, please.
Yeah.
Yeah, I think these are absolutely beautiful, and you should submit these to a competition like NSERC Science Exposed. I think you'd have a real good chance.
Thank you. We very much like these pictures, and there are some plans to try and do that. We're just trying to find the perfect picture. We're still not 100% happy with how this turned out, and we think that we can do a little bit better with this. So, but thank you very much.
Yeah, they all look perfect to me, especially the ones on the left side.
Thank you.
Are there any other questions from the audience?
I don't have a question, but I would add to Shim's comment. Yeah, the images are beautiful. They're like great.
Thank you.
Okay, Sebastian, I'd like to thank you very much for rounding off the season of the Young Researchers Forum. For everyone else, thank you for coming. Thank you for participating throughout this year. So we're trying to be back in the fall or next winter with the 4th season. So if you know anybody who'd be interested in presenting, or anybody that you think should present, please let us know, and we'll try to reach out to them. We're looking for usually people who are finishing off their PhD or who have recently finished that off, to give a presentation on a broad ranges of topics that they've researched and tie it all together into one story. So again, thank you everyone. I hope to see you at conferences this summer. I'll be at ICTERS in Korea. And if I don't see you then hopefully we'll see you next year at the next season of the Detonation Forum. Thank you very much. Thank you, Sebastian, again.
Thank you.
Thank you.